Okay, in this video we're going to just introduce how we deal with capacitors when they are in parallel in a circuit. So you've seen this drawing similarly when we had resistors, and it is very much the same kind of idea. We have a branching point through which we connect two capacitors and then bring them back together here. And this is a classic sort of capacitors in parallel scenario. Now, what we're going to do is we're going to ask the question again, what does it mean to have charge conservation in this? And so what this suggests to us is that there's not a current flowing, because otherwise we'd be in a non-steady situation, and that's problematic. But that there is some available charge associated with the battery, and that available charge gets pushed out onto the capacitors. And the total sum of Q1 and Q2 is equal to the total charge that the battery is able to sort of supply. And this will come back when we talk about this idea of equivalent capacitance. There's no need for these two things to be the same. They can be different from each other. That's totally fine. And so what we're going to do is then apply the potential energy per unit charge around the loop. Noticing that they are in parallel, we were going to have one loop, which is this inner loop that goes through capacitor 1. And then we will have a second loop that goes through capacitor 2. In that first loop, whatever the potential difference is across that battery is going to be equal to whatever the potential difference is across capacitor 1. And whatever the potential difference is across the battery in loop 2 is going to be equal to whatever the potential difference is across capacitor 2. Okay? So what we can do is we can think about this in terms of the capacitance in this situation. So each of these is going to be equal to its own charge, Q1, divided by its own capacitance, C1, and similarly Q2 and C2. Now what we want to do is we want to be able to replace this with an equivalent capacitor, because that often helps us to deal with problems. And so what we're going to have is instead a single capacitor, which we will refer to as having C equivalent capacitance. It's hooked up to the same battery. But what do we mean by equivalent in this case, right? Equivalent means that the same amount of charge is stored on the equivalent capacitor. That's what we said earlier. That's what we're saying now. So that means that if the battery can supply Qbat, that's exactly what's stored on both of those capacitors. So Qbat is Q1 plus Q2. So the equivalent capacitor will have Qbat, which is equal to the equivalent capacitance times delta Vbat. But it's also equal to Q1 plus Q2. That's the total charge that's stored on the batteries in the real situation. But each of these guys, Q1 and Q2, is exactly the capacitance of each of those capacitors times delta Vbat. Or written in the math, the equivalent capacitance times Vbat is going to be equal to C1 times delta Vbat plus C2 times delta Vbat. All of them share the same delta Vbat, so C equivalent is C1 plus C2. And again, this holds for any number of these that are in parallel like this. Now, this is actually a little more intuitive than the last one, because what we've done is essentially effectively spread the area of the capacitors out. We've made larger area capacitors, and so we expect the capacitance to go up in that scenario. So that makes a lot of sense with our sort of microscopic perspective of what capacitors actually look like. So what we did here is essentially just apply conservation of charge and conservation of energy to a system consisting of two capacitors in parallel, and we were able to derive the equivalent capacitance, namely that they just add like you would expect them to add, C1 plus C2 plus C3 and so forth.